Hello. Today my team and I will briefly talk about the scope of our project for the TiM 10K challenge. The motivation behind this project is to prevent injuries by reducing power mobility device accidents. As you can see, more than 100,000 accidents have been recorded by the American Emergency Department in 2003, and most of them are due to limitations of movement by users of those power mobility devices. The TiM's product aims to prevent accidents by detecting potential dangers and alerting the user. This will be done by attaching a universal SICK LiDAR sensor to a power mobility device to increase user autonomy and the ease of life.
To be more specific, the team designed a multi-alert feedback system using a SICK LiDAR sensor in order to alert a PMD user of any obstacles or terrain changes while reversing. The system is designed to alert the user of any obstacles and elevation changes of 3 inches or greater with a range up to 6 feet. Once detected, the system will alert the PMD user via a flashing LED and vibrating watch. This feedback system will give the user enough time to stop and/or change paths in order to avoid disaster. The team decided on a dual feedback system in order to make the system more reliable and accessible. Studies have shown that people responded better when there were multiple types of feedback systems. In addition, the dual feedback system would be able to accommodate more people. For example, if a user's vision is impaired, the vibrating watch would still be able to alert the user.
For the mechanical design, we wanted to create a mounting system that was universal for all PMDs. As you can see in the video, that has the exploded view of the complete mounting system with all its components. With the picture, you can see the mounting system placed behind the PMD in order to detect any obstructions. The LiDAR sensor was mounted on its side so that the sensor could scan vertically. This was done to ensure that the sensor would pick up obstacles as well as elevation changes. Our application required a 3D scan of the terrain from a 2D sensor. In order to get information needed of the surrounding 3D environment, the sensor was attached to an apparatus that would allow it to rotate horizontally with the use of a stepper motor.
A visual representation of how our application detects incoming obstacles and elevation changes is shown. It starts with the sensor publishing data and then traversing through the data looking for potential dangers. The two ways to activate the alert systems are 1, if any single data point is less than 2 meters or about 6 feet away, or 2, if the difference between two neighboring data points is greater than 0.075 meters or about 3 inches. This happens for every data scan, so it will continuously operate as long as the sensor is outputting data.
Unfortunately, due to campus policy changes put into effect because of COVID-19, the team was unable to finish assembling the final prototype. However, we were able to complete several feasibility tests. Both of these tests show the integration of our feedback system, the LiDAR sensor, and the detection algorithm. In the terrain change detection video on the right, our Raspberry Pi is connected to the LiDAR sensor as well as an LED. While there is no elevation change, the LED remains off. When the chair is rotated, the LiDAR sensor begins picking up the elevation change of the stairs, and the LED begins blinking to alert the user of an elevation change. The images on the left show our obstacle detection tests. While the LiDAR field of view is clear, the LED remains off. Once a hand obstructs this field of view, the LED turns on to alert the user of an obstacle.
Excluding the price of the LiDAR, which retails for around $2,500, the final product was designed to be as cost-effective as possible. As seen in the pie chart, the total spent on other components was around $480. As the price of personal mobility devices can range anywhere from $800 to $3,000, it was important to reduce the cost of the final design to make the product more marketable to PMD users. According to a study performed by the Education Resources Information Center, mobility device users of all ages are very likely to have some form of health insurance to pay for their PMD. It is hoped that with the product's unique universal design, the product is able to be approved by healthcare companies for insurance coverage. On top of power mobility devices, it is hoped that the product can also be marketed for other transportation devices such as golf carts and scooters due to its universal design. Research was conducted and found that the number of golf cart-related injuries in the U.S. has increased over 132% in the last 17 years. Likewise, a different study found that nearly 40,000 injuries were treated in U.S. emergency rooms over the past 4 years due to electric scooter accidents. Overall, it is hoped that the final design can be marketed towards devices such as these at a reasonable price in order to increase the safety of everyone involved.